Hi everyone. So today we're going to get started on our last topic for the quarter, which is something called antiderivatives. So antiderivatives are actually a big part of what you'll be learning about in Calculus 2. So if you're taking that next, you'll see a lot more of what we're going to be talking about for the remainder of this week. So the general idea with antiderivatives is that basically it's just working backwards. So far we've generally been in situations where we know our original function and we're trying to find the derivative. And so the idea behind antiderivatives is basically just kind of reversing that process. So being handed a derivative and trying to figure out, what function did this derivative come from? So let's look at an example to start with. So I would encourage you to try this example yourself before we go over it. So I want you to think about if, let's say I tell you that f prime of x is equal to 2x. I want you to figure out what is the original function f of x. And so this might sound like a simple question, but if you're trying to come up with your answer yourself, I would encourage you to see if you can come up with a few different answers that work. Okay, so what's the answer here? Well, the first answer that you might have come up with is f of x is equal to x squared, right? Because when you take the derivative of x squared, you get 2x. But there are other answers that could work, right? You could say f of x is equal to x squared plus 1. That would also give you a derivative of 2x because the plus 1 is not going to affect the derivative. You could also say f of x is equal to x squared minus 100. Because again, the negative 100 is not going to affect the derivative. So these are all examples of antiderivatives of our function f prime of x is equal to 2x. So there's a way that we can kind of summarize this idea, right? Like when I just told you f prime of x is equal to 2x, that wasn't enough information for you to determine what f of x was, right? We wrote down 3 different examples. There's infinitely many examples, right? You could tack on any number you wanted and that would be an antiderivative. So in order to kind of summarize all of those different possibilities, we write it as follows. So we can summarize these possibilities as saying f of x is equal to x squared plus c. And so when we write plus c in this context, c represents any, and let me just use a different color so this stands out a little more. So here this number c represents any constant. So a positive number, a negative number, any number that you want to tack on at all is a possible addition to your antiderivative. And so when you write it this way with the plus c, this is what's called the general antiderivative of our original function. So all the examples we gave here were specific examples, but typically what we'll be doing in today's video is finding the most general antiderivative of a function. And so you're always going to want to add on this little plus c. So I just want to visually kind of give you an idea of what we're looking at here. So when we say plus c, so x squared plus c, I typed this into Desmos and I added c as a slider so that I could change the values of c. And we can see that no matter what number c is, the graph is shifting up and down, but the shape of the graph isn't changing. And so it kind of makes sense that you can always add on plus c to any function and you're not going to change its derivative. And so if you're trying to find an antiderivative, that's why you can always include this plus c, because it's just not going to affect the shape of the graph, and the shape of the graph is what dictates its derivative. Okay, so I just want to kind of summarize or generalize what we wrote down there. So in general, actually, let me scroll back up to this for a second. So this was an example of a problem where I started by telling you f prime of x equals 2x, and then you said, okay, the antiderivative is f of x. But sometimes the original function you'll be handed will be written as f of x. And so we need a new notation to refer to the antiderivative of that, right? We can't just add a prime because that would be kind of backwards of what we're supposed to do. So if you're trying to find the antiderivative of a function that doesn't have a prime symbol on it, we now have this new notation we'll use, which is just going to be a capital of whatever letter was used for the function. So I'll write that down below. Basically, it's just kind of a notational thing. So in general, so we can say that f of x is the antiderivative of f prime of x. And then if you want to go further, or if you're trying to take the antiderivative of f of x, then you use capital F of x. So capital F of x is the antiderivative of little f of x. So I just want to kind of summarize that with kind of a diagram here. So basically, if you have the function f of x and you take the derivative, so you take the derivative, you're going to end up with f prime of x. And so what that means is that if you take the antiderivative of f prime of x, that is little f of x. So if you wanted to take the antiderivative again, that's what we were talking about just above. That's where you use the capital F letter. And so if you take the derivative of capital F of x, that's going to give you little f of x. And this isn't like super duper important. This is just kind of the standard notation, but usually you'll be able to tell by context, right? Like usually the question will say, find the antiderivative of this. And I don't even really care that much what letter you use, but the standard is basically what's written here. Okay, so I want to get into basically kind of like the most important examples of antiderivatives. So this is another one I want you to pause and think about yourself. And the reason I'm going to ask you to pause and think about this yourself is basically that, especially when you're taking antiderivatives, I think like the best way that you can possibly kind of gain an understanding of how they work is by guess and check, by trying something. And you can, the nice thing about antiderivatives is you can always check your work. You can always take the derivative and see if that gives you the right thing. So I really think that's a great way to make sure that you're not just kind of doing a superficial memorization thing with this, but really kind of understanding why things work the way they do. So what I would like you to do is to find the antiderivatives, and I'll say the general antiderivatives because we want to include that plus c. And let's just do f of x is equal to x squared, and g of x is equal to x cubed. Okay, so if I were learning this for the first time, and if I were trying to guess what I thought the antiderivative was, I think a reasonable first guess might be x cubed. Right? Because we know how the power rule works. We know that when you take the derivative of a function, you bring down, or you subtract 1 from the exponent. So let's check that and see what happens. So if we were to take the derivative of this, we would get 3x squared. But that's not what we want, right? We want, our original function was just x squared. And so we don't want this there. So we need to figure out how to kind of get rid of that. So how can we ensure that there's no 3 showing up there? Well, we can counteract it by putting 1/3 here. And then I forgot to put plus c. So why does that work? Because then if we take the derivative, we get 1/3 times 3x squared. And then the 3's cancel out and we're just left with x squared. And that's what we wanted. That was our original function. And so similarly, if our original function was g of x is equal to x cubed. So in this case, the antiderivative, we could call it capital G of x. So again, we know that the exponent has to be 4, right? Because when you're taking the derivative, you're going to subtract 1 from that. And so that will, to get a 3, you need a 4. But just like before, we need to make sure that when we bring that exponent down, it doesn't give us anything extra here. We want just like a coefficient of 1, basically. So that means that we have to put a 1/4 in order to counteract the 4. So we can kind of summarize this as a general rule for antiderivatives. You can think of this as kind of a reverse power rule. So let me say it this way, the antiderivative of f of x is equal to x to the n is going to be capital F of x is equal to, so the new exponent will be now n plus 1. And then we need to then multiply that with 1 over n plus 1. And then I should throw on a plus c here. So we'll see that there's kind of one exception to this, and we'll get there in a moment, but I want to first do a few examples of actually using this. So one thing I just want to point out here that I think will be useful when you're actually taking antiderivatives is that 1 over n plus 1, that's the same thing as the reciprocal. So this here is the reciprocal of n plus 1. And so the reason that will be useful for some of these is that if your new exponent is a fraction, then rather than write 1 over a fraction, you can kind of just jump straight to writing the reciprocal of that fraction. So let's do a few examples using this new kind of reverse power rule. So let's say that we are trying to find the antiderivative of f of x is equal to square root of x. Actually, before that, let's even do kind of a simpler example. So let's say x to the 100. So what would the antiderivative be here? Well, we would add 1 to the exponent, right? So we would make this x to the 101. And then we would multiply that by 1 over our new exponent. And then we tack on plus c. Okay, so next example, let's try square root of x. So just like with taking derivatives, with taking antiderivatives, you want to rewrite it as an exponent. So we can rewrite this as x to the 1/2. So what's the antiderivative going to be? Well, we want to start by adding 1 to the exponent, right? And I'm going to scooch this down so that we have space for me to add a few notes. Okay, so we want to start by adding 1 to the exponent, and I always recommend doing that first. So maybe just kind of leave a space and first figure out what the new exponent is. So the new exponent is going to be 1/2 plus 1. So 1/2 plus 1/2 plus 1 is equal to 3/2. So this is 1/2 plus 1. And then how do we get the coefficient here? Well, we could write 1 over 3 over 2 and simplify it, but the shortcut is just to remember that it's just going to be the reciprocal of whatever number is there. So what's the reciprocal of 3/2? It's 2/3. So this is the reciprocal of 3/2. And so that's why I think it's better to first find the new exponent, because then you can just take the reciprocal of that and put that as your new coefficient. Okay, so let's do a couple more examples. So next one will be 1 over x squared. So how do we write that in an exponential form or a kind of power form? We write it as x to the negative 2. So the antiderivative, if we follow the rules, is going to be, so the new exponent is going to be negative 2 plus 1. So that gives you negative 1, right? So this is negative 2 plus 1. And then we don't really have to write anything here because, we do, but it's going to be the reciprocal of negative 1, right? Or 1 over negative 1, which is negative 1. So I'll write that down, but then we can actually just write that as a negative sign. I feel like I don't really have to write any notes there. And then we have plus c. And I forgot plus c on this. I'm probably going to forget plus c on some of these, but you shouldn't. So if you wanted to, you could actually rewrite this as negative 1 over x plus c. And that should kind of make sense to you because at this point, if when you've done derivatives a bunch, you probably have started to recognize that the derivative of 1 over x is negative 1 over x squared. And so we basically need this extra negative sign to cancel out so that you're just left with 1 over x squared. Okay, I want to do one more, and this one is kind of a trick one. Okay, so 1 over x. So I want to see what would happen if we tried to do this using this reverse power rule, but we would basically see that it doesn't work. So if we rewrite this as x to the negative 1 and see kind of how that plays out. So if we try to use the reverse power rule, we start by adding 1 to the exponent. And so if we do negative 1 plus 1, we get 0. So that should already seem a little wrong, right? Because x to the 0 is 1, right? Any number to the 0 is 1. And the derivative of 1 is not 1 over x. So that already seems a little fishy. And then also, we're then supposed to take the reciprocal of the new exponent. So this is supposed to be 1 over 0, and that's undefined. So this just doesn't really make sense. So I want to add to this rule that we wrote up above that this rule is only for, so this is for all n not equal to negative 1. So as soon as that exponent is negative 1, you can no longer use this rule. So why not? Well, basically there's a simpler answer here, right? So think about what an antiderivative is. An antiderivative is basically just asking you to work backwards. So what is the function that when you take the derivative, you get 1 over x? Well, and I'm going to write something here. Well, I'll write it like this for a second, and then we'll come back to this, and there's actually a slight change we have to make. So ln of x plus c. So why is it ln of x? Basically because, well, the derivative of ln of x is 1 over x. So there's one small change we have to make here, and it's a little confusing, but basically just something you have to remember, which is that the antiderivative of 1 over x is actually not ln of x, it's ln of absolute value of x. So why is that? It's basically because so what kind of numbers are you allowed to take ln of? They have to be positive. You can't take ln of any number that is negative. It just doesn't make sense because ln is asking you what power you have to raise e to get a number, and you can't raise e to something and get a negative number. So you're only allowed to take ln of positive numbers. And so when you're just dealing with the function ln of x on its own, it's kind of assumed, it's like built in that the domain does not include negative numbers. But if your original function is 1 over x, there's no assumption there. Like the only thing that is excluded from the domain there is 0. And so if your original function is 1 over x, that could include negative numbers. And so basically you put this absolute value in to kind of force ln to be defined. So I'll make that note here. So we include absolute values, include absolute value. Actually, I'll just write the word because I feel like that's a little confusing. So you're going to include absolute value to basically guarantee that ln is defined. And so that's going to be always the case. Every time you're taking the antiderivative of 1 over x, your answer should not be ln of x. It should be ln of absolute value of x. So that's really important. It's something that a lot of students forget, but try not to forget it. Okay, so I want to do a couple examples now kind of that are a little bit more complicated, just like pulling together different functions and finding the antiderivative. Oops. So I'm not going to go over like every different possible antiderivative that could come up, because it really is just working backwards and thinking like, what function do I need to take the derivative of to get this? So what I'm going to do is, on your worksheet for today, I'm going to give you a table of common functions that you should know the antiderivative of, and I would ask you to fill that out, and then I'll go over it in tomorrow's video. But yeah, like I said, I just think the more you can kind of try to come up with these things yourself, the better off you are than trying to feel like you're memorizing everything. Okay, so let's say that, or I'll just say, find the antiderivative of So let's call our function g of x is equal to 3 over x plus 7x squared plus 5. Actually, I'm going to make one more complicated thing here. Let's actually, sorry about this. I'm going to say minus square root of x plus 5. Okay, so just like with derivatives, with antiderivatives, because they're just kind of like the reverse of derivatives, you can go through and take the derivative of each term individually. And then the other thing that works just like derivatives is that when you have a constant, so for example, here we have 3, so this is the same as 3 times 1 over x, or here where we have 7 times x squared. In those cases, you can kind of pull the constant aside and take the antiderivative of the remaining part and then just multiply it in at the end. So I'm just going to kind of rewrite this function with that in mind. And it's basically going to look exactly the same, but I'm just going to separate out that 3 from the 1 over x and then really kind of just emphasize how we're not going to focus so much on the constants, and then I'll write the square root of x as x to the 1/2, and then we have plus 5. Okay, so what is the antiderivative going to be? Well, we saw above that the antiderivative of 1 over x was ln of absolute value of x. And so that means that we can put ln of absolute value of x here, and then we can multiply it by 3, right? Because if you take the derivative, you'll get 1 over x, and then then you multiply by 3 and you get 3 over x, which is exactly what we had. So you could say plus c at this stage and then keep saying plus c every time you take an antiderivative. But what we're going to do instead is we're going to kind of group up all those plus c's and just put them together at the end, right? Because the plus c represents any number being added. And so there's no reason that you need to add those numbers all individually. You can kind of lump them together and just add them on at the end. Okay, so we have 3 times ln of absolute value of x. So next part, we're going to take the antiderivative of x cubed. Of x squared. I kind of got a step ahead. We saw above that that was 1/3 times x cubed. And then we're going to multiply that with 7. Okay, so next part, we're going to take the antiderivative of square root of x. So we saw that that involved adding 1 to 1/2, and so that gives you 3/2. And then taking the reciprocal of the new exponent, and that gives you 2/3. And then what about this 5? So what is the antiderivative of a constant? It's not 0, right? The derivative of a constant is 0, but the antiderivative of a constant is not 0. So just think about it as like, what function could you take the derivative of and get 5? And the answer is 5x, right? Because if you take the derivative of 5x, you just get 5. And now we can tack on this plus c, and it's kind of this general constant that you could have written it specifically for every piece, but might as well kind of throw it together at the end. So putting this all together, we have 3 times ln of absolute value of x plus 7/3 x cubed minus x to the 1/2, because the 3/2 and the 2/3, or sorry, I just started taking the derivative for some reason. My bad, sorry. I was thinking about telling you to check your answer by taking the derivative, and then my brain just started taking the derivative. But I was just trying to rewrite the function a little more nicely. So this is our antiderivative. But yeah, what I was going to say next is that you can totally check your work by taking the derivative of this. And I would really, really encourage, especially, if it's on like a test or quiz or something, I would recommend that you do that. There's no reason not to, basically. It's just going to, ensure that you kind of did your work correctly. All right, one more example. So we're going to find the antiderivative of g of x is equal to -3 square root of x plus x cubed, all divided by 4x. So first thing I want to get out of the way is that there is no such thing as like the reverse quotient rule. So that's not how you can go about doing this question. It's also definitely not the case that the way that you should definitely not do this is by taking the derivative, the antiderivative of the top and then taking the antiderivative of the bottom and just kind of smushing them together. It doesn't work that way, right? That's not how we take derivatives, so it's definitely not how we take antiderivatives. So what we're going to do instead is split this into 2 fractions. So this is something that I encouraged basically all quarter with taking derivatives, was that if you have a function that can be kind of split up and simplified before taking the derivative, then you should do that. And some of you have done that, a lot of you have not done that. But with taking derivatives, it's kind of optional, right? If you were asked to take the derivative of this function, you could use the quotient rule and that would be fine. It would be more work, but if you didn't realize that you could simplify this, you could totally just use the quotient rule. However, when you're taking antiderivatives, really the only way to take the antiderivative of this is to recognize that it can be simplified. So that's really the main reason that I was kind of pushing you throughout the quarter to simplify stuff before taking the derivative, is because when we get to antiderivatives, that idea is even more important. So how can we split this up? We can rewrite it as -3 times the square root of x over 4x plus x cubed over 4x. So why is this helpful? Because now we can simplify each of these pieces individually. So we can rewrite this as -3x to the 1/2 over 4x plus x cubed over 4x. And now we can use exponent rules to simplify each part. So what are we going to get? In this case, we'll get -3/4 x to the -1/2, because we are doing basically x to the 1/2 minus x to the 1. And then what do we get for this next one? Well, we get 1/4 x cubed, x squared. Okay, so we did not do any antiderivatives yet, right? All we did was we rewrote our function a new way, but now we're ready to take the antiderivative because now everything is set up to use the power rule, or the reverse power rule. Okay, so I'm going to just kind of take that -3/4 and just kind of put it to the side for now, and leave some space for the coefficient, and let's figure out what the new exponent is. So to get our new exponent, we're going to take -1/2 and add 1 to it. And so if you do -1/2 plus 1, that's going to give you +1/2. And so what do we do now? Now we multiply by the reciprocal of 1/2, which is 2/1. So next part here, we have 1/4. I'm just, again, going to kind of pull that to the side. And we're going to take the antiderivative of x squared. So that's going to be x cubed, and then we have a 1/3. And then we have plus c. So let's clean this up a little bit. So we're going to get, for this first one, we're going to get, so we can simplify here, this 2 and this 4, this can become a 2. And so we'll be left with -3/2, x to the 1/2. And then here we'll have plus 1/12, x cubed, plus c. And if you wanted to, you could then rewrite this as a square root of x. I'm just going to leave it like this for now. So yeah, that's basically it for today. Like I said, I really encourage you to check out today's worksheet and try to fill out the table I'll give you with some other antiderivatives. And tomorrow we'll do a little bit more practice with antiderivatives and also some examples of questions where you have to find not just the most general antiderivative, but one specific example of an antiderivative. All right, I will see you next time.